after I find this, I will back to it. When we get acquainted, then the start. I have to get acquainted.
It's quite a rough transition between the two time zones. So, okay, Anchorage design. You guys probably know some about it already, or maybe not. If you guys been helping with Anchorage systems, have to do something with Anchorage. Ours is a little bit different, but most of them are the tension is per ACI 318 Appendix D for tension. For shear, depends on which model we use. One of them with the shear lug, we're actually doing a ASC design guide 1. Let me get I have a model there. This is what I'm talking about. Okay, that's our one with the Anchorage kit. This is the shear lug. What we're talking about. That's the angle. Okay. And this plate is where we have in the top one. This plate is where we ship so we can measure it. That's basically embedded, so they're pulling up. This is for shear only. So when I go through it, I need to use the different components, but that's what it looks like in real life. Okay, we'll do the frame base detail, and then followed by the different foundation types and anchorage models. We'll see what we do with tension anchorage and shear anchorage, and then how do we handle combined tension and shear. Okay, that's and then followed by review. So our frame base detail is what we're trying to do is basically anchor our frame down to concrete. The basic what we have is for the SMF is 4 3/4 inch diameter anchor rod. We have a non-shrink grout underneath the base plate. Okay, here's the steel column, and here is the steel base plate. Okay, so there's a grout underneath it. This is the angle that I was talking about. You guys just saw. Depends on what model. This would or would not be there. Yeah. Okay, and that's the purpose of it is for shear, and I'll go into that when we do the shear anchorage. So the base plate detail, we try to keep this somewhat close to 3 inches. Again, mimic the pin behavior, like what we talk about. The holes are typically 1 inch. These patterns are 3x3. However, one project when we had a big column, the web was pretty thick, so we actually have to spread out this to be, instead of 3, I think we spread out to like 4 or 5. Okay, because this column was like 12 inches or something, whatever. It was very wide when we had to size it. So is this dimension, you could probably keep it 3. Go in that direction. If you detail it, then they will fabricate it whatever you need. Okay, so the basic pattern is 3x3. The hole size is 1 inch. Anchor bolt is 3/4. So you can see our holes are oversized by 3/4 of an inch. Okay, for typical bolt connection, not the anchor bolt, typical bolt for steel beam, the column, steel construction, the hole size is 1/16 over. Okay, so what now we're over that, and they allow a bigger size for the base plate is because you have anchor bolt for tolerance. You always anchor bolts are not always straight, it's always out of tolerance, and they cast it wrong. And that's why we also offer as a kit, is because we want them to be pretty fixed from one to another. So we sell two, one on one end, one on another end. When they cast in the concrete, this is all buried. All they have to do is drop the columns in here, tighten the bolt, and that's good. Okay, so that's the base plate detail for the bottom. We have a lot of different conditions. This is the slab on gray. This is taken directly from the software. You've seen it before, but I just want to utilize this to pick up or show some of the elevations of what they look like. So for the slab on gray, we have two solutions. We have the MFSL and then MFAB. MFSL, MF is the moment frame. We used to have OMFSL, but we condensed it so we could use it for both lines. So now it's MF, moment frame. SL is shear lug. Shear lug is this thing. I'm calling the angle as the shear lug.
Shear lug.
Yeah, I'll show you the spelling later. It is a lug, so shear lug. Okay, so that's slab on gray. The second method is the AB with the hairpin. So if you see the difference here, look at the picture. You have this here. This one, we don't have it, but you have the ties that ties it back to the slab. Okay, so this is foundation slab on gray. Next one is curb, kind of garage front or kind of a wall when you're looking at it. Then when you put it on top, the curb is short. Okay, when you talk stem wall is a little taller. That's why we have a couple of differences. So MFSL as well, and when you have a tall curb, now you're not only transferring shear per se, we're looking at as a kind of cantilever column, almost a little concrete column. Then you're looking at, especially when you're bearing that direction. Okay, compression a little bit, and your concrete is not helping. This is your tension rod. Now I'll go through and see how we actually calculate some of these anchor capacities. For your tall ones, a stem wall. Stem wall is very short, very tall compared to your curb. Okay, they start out with like 30 or 46 inches, 48 inches, whatever, or even more if you do it for a basement wall. So on this one, we only offer the OMFSL solution because the ties and the wall bars, they could probably use it and account for the wall bars for the shear transfer. So we only offer this one. Two solutions: the MFAB, MFSL, as you see, very much similar, except the only thing.
Let's on the side we get for the job site.
This the place for job site replacement. Yeah, placement. Oh yes. So we have some slots here. There's only one slot now, center slot. So they actually take measure from one end, go to take measure from another end to locate their center spacing. And this one you don't see it because somebody put a plate on the top, but you can also use these as handles to carry it. Okay, so that's what they are locating. I'll cover tension anchorage first, followed by shear, then tension and shear. For tension, essentially, most of the components is per ACI 318 Appendix D. Okay, 1808 or 11, I don't think there's much difference for our concern. So I'm going to just say ACI at this point. So the one is embedded plate bending, and that's the AIC calculation. Embedded plate is the bottom plate down here. Okay. So we're pulling on it. So that's bending. If you imagine this plate to be wide apart and wide apart, when you pull on it, the plate is like sack is going to bend. Right. So that's first mode is bending per AISC. The second mode is the steel capacity. The third is concrete breakout, followed by pull out and side face blowout. All these are directly from AISC, the appendix, ACI 318 Appendix D. Okay. So the first one, capacity and tension, is the embedded plate. So what we're trying to do is just make it as kind of a standard washer. We have some equation to calculate it, and then here is the load per anchor. So we have a 3/8" plate, so it's actually 0.375. It condensed to that, and then these plates are just 836, so grade 36, and the capacity for this per angle is 38, almost 40,000 pounds. So times 4, it's a lot of capacity. Okay, so that this mode does not control compared to the other mode. Okay, but we still have to show it that it's show the calculation, show what the capacity. The second mode of failure is steel capacity. This is directly from ACI, and this is even from ACI, so just showing you what they are. So 5.1 is steel failure, and then basically N times AISC times FUT. The difference between ACI and AISC, this A is actually you have to account for the thread. So they publish that area. Versus ACI, when they say the bolt, they just account for the non-reduced area. Okay, this is the two difference between the two agencies, how they view the area. FU here, ACI do not reduce by the 0.75. So whatever FU they publish, you use the true FU. So pretty easy. Number of anchors times area, effective area times FUT is your NSA. That's the steel. Concrete breakout is when you're basically breaking out the concrete. Okay, this is a lot more involved with a lot of fee factors, a lot of factors associated with the spacing, group behavior, and all that. So D 5.2. 5.3 is the pull out. Okay, for pull out, basically the NP for a single headed stud, they give you an equation of what that is. For blowout, 5.4, if you're close to the edge, this could come out. Okay, it's blowout. For shear anchorage, okay, that's it. I didn't show you how to calculate, or we actually also have a spreadsheet, and I embedded into the base plate design, so you could take a look at it to make sure it works. It hasn't been back checked. It's just for my own calculations for that. But the shear lug anchorage, you have AISD design guide 1 for the shear lug, so LUG, that's what the shear lug. MFAB, MF moment frame, anchor bolt. So no shear lug. Okay, very innovative naming. Anchor bolt only. This solution you could do it with hairpins or with ties. Hairpin is you bend it in the field, in the slab. Yeah. They call it just a pin. Like a loop. We'll see what it looks like. Okay, and then this is ties. Ties usually tie around. Okay, so the first one is shear lug at slab 1 grade. Yeah, this is for design guide 1. What we're trying to do is to increase the concrete cone, the breakout, by adding something to the bottom to enlarge the concrete cone. Okay, if you're looking at this is the edge of slab, this is internal, so here's the shear lug, you're pushing on it. Okay, here is the effective area. The effective area is basically the angle plus the width is, and plus AB. AB is this. So this is 1 to 1. That obviously AB is just this plus that to the center line. Design data angle size is a 3 by 3 by half, 3, 3, half, and then 5-inch long, and then the K area. So that's the breakout area. So essentially this, you can picture it, a 3D breakout of this cone, and that's your shear capacity. For the curb, it's pretty similar. Instead of projecting out, we're limiting this to the width of the curb. So you can't go more than the width of the curb. Okay, shear anchorage, like I say, we have a design spreadsheet that takes care of it. You'll have to adopt it to your design. I'll show you what to do. Maybe even update some of these like OMFS numbering on the spreadsheet. So calculate the effective stiffness. Calculate your design guide with the bearing, the pressure, X, the edge distance. Here's the shear area, AV. Okay, we have step by step that spells out, and also on the bottom we have I'll show you in the spreadsheet. It's easy to read. We have all these noted step 1, step 2 across to show how we got those capacities. Okay, so we check the angle at the base of fillet, we check the angle at the toe, and then we check angle bending capacity. So basically, first all these check are per design guide 1 and AIC 360. Hairpin, this is the hairpin I'm talking about. Okay, that's called a hairpin. This one is you have shear applying this direction, right? What we're trying to do is hold back this shear. That's all it is. So how to design these is AV is number of hairpins times ASFY. Okay, what we're using is hairpins are number 3 bars. You don't want it to be too big because they bend these in the field. If it's too big, they cannot bend it in the field. Okay, so that's this. This one is resisted by that one. That's the shear capacity. So when you do that, the concrete do not break out, right? That's what we're trying to do, is to tie it back. For the OMF AB with ties, because it's a bigger curve, if you bend this way, we assume there's going to be a moment, and then the shear is resisted by the tie. The moment is by the vertical bars. So when the moment bending, you have this tension of the steel. So we're accounting for that steel, and then we're compression. Here's a compression block. So you size the curve for both shear and bending. Shear is taken by the ties. Bending moment is taken by vertical bars. And I'll show you a blow up of what that D would be, the lever arm we're talking about. Okay, so that D is from edge of this, if you look at this side, it's the same thing, to the vertical bar. That is the D. Okay, S is the tie spacing between this. So again, we have somewhere in the spreadsheet that tells them how we calculate the different design strength. So we have the structural strength. There's a compression block. So you use the concrete calculations. You have the A1. There's compression block. Then you get the design strength of the curve, and you back out what the V is, and then now you also the tie reinforcing. That's what the S is. D, you already know. FYT, you know. AV, you know. VV, you know. So we could calculate all these, and at the end we take the minimum as our shear strength for this tie assembly. Okay, so that's the ties, MMFAB with ties. Shear and tension anchorage is a tough one. Our default right now is we don't deal with both shear and tension. We assume tension cone to be in the footing. Okay, assume your shear to be taken by the slab. So as long as you get your shear into the concrete, that's taking the shear. Tension is taken care by the footing. Okay, assume no interaction between the two. What that means, the failure cones do not overlap. What happens if they do overlap? Okay, so if your failure cones do overlap, then we recommend using a supplemental reinforcing per ACI. Okay, what that supplemental reinforcing is, these is what's per ACI. Okay, so we have a spreadsheet that does this one, and once if you put in supplemental reinforcing, then one of the failure modes you don't have to consider. Okay, it's this one, the design strength of the anchor reinforcement shall be permitted to be used instead of the conquer breakout strength when you're calculating shear. So you could reinforce that, and after you reinforce it, then you could probably check tension and shear interaction. You still need to check it, obviously, but no, right now our default is this. But if somebody wants you to check that, then yeah, you could still do it, but we'll need to provide some supplemental reinforcement. Okay, so that's what it is. Bearing pressure and footing design. We don't know what the bearing pressure is, okay? It's a lot of engineers trying to ask you to design this for them, and we keep saying no. Okay, so we leave it up to the designer to design a concrete foundation, also the designer to check the bearing pressure. Okay. Do you guys need to get in right now, Jim?
No,
We'll be done in 5 minutes on this, and then we're going to move out. Right. So, review. Right now, Simpson Strong Tie offers two types of the Anchorage, MFSL and MFAB. The SL comes with the shear lugs. The MFAB requires field install ties or hairpins. Anchor plus shear of anchor bolt was calculated as part of the base plate design. Okay, remember when we check the anchor bolt above concrete, we check both shear and tension. So that we do consider interaction between shear and tension. But when you get to the concrete, is depends on what the concrete footing condition is. The failure cones might or might not overlap at that time. So our default is, okay, we assume it to not overlap and give you the capacities of both tension and shear, and to check that. However, if they do overlap, you should take care of it. We recommend them take care of it with supplemental reinforcing. Okay, so no tension shear interaction capacity is assumed. We encourage the designer to take care of the use supplemental reinforcement to take care of the tension plus interaction of the concrete capacity. We only offer Anchorage solutions. Okay, soil design, foundation design, and bearing pressure check should be done by the designer. So when we say only offer Anchorage design, we would tell them how thick the concrete, how wide the concrete, how much embedment. But yeah, that footing, if they need to check by, okay, bearing pressure check. If bearing pressure check increases by quite a bit, then they would have to design the footing themselves. Okay, that's pretty much Anchorage design, and I'll show you our Anchorage design Excel spreadsheet now, just to cover the.
See you guys later.
Okay.
See you Monday.
Sure. Yep.